And welcome to the Austin Python Meetup. We're very happy to see many of you today, even though there's COVID-19 out there. And we have two presentations related to data and GPUs. The first one is from Taurean. Taurean is from NVIDIA, and he's coming to us actually from California, so he's online from California all the way. And then we have Michael, who is going to talk about
William,
who's going to talk about BlazingSQL. Sorry, Michael, for confusing you. Michael got
William for confusing.
No. Michael was talking before, so he.
Good times.
Okay, so still people are arriving, but hopefully they won't arrive many more. So Taurean, I'm gonna go ahead and ask you to take over the presentation and give the first presentation. And if anyone has questions, jump in, unmute yourself and ask questions. Otherwise, please remain muted. Here we go, Taurean. We see you very nicely, but we don't see you, but we see your presentation, which is good.
Oh, beautiful. Okay. So, hey everyone. My name is Taurean Dyer. I am a technical product manager at Rapids. It's really exciting to be here. I haven't been in Austin. Actually, I was in Austin last year for a galvanized meetup, and I'm kind of missing getting some barbecue right now. But today, I just wanted to check in with you. We like to have a very interactive presentation. There's a chat window on the side, so you can message and kind of hit, messages back and forth so we can see things, or just even nod your head, like especially if you're on video. But just quick questions for you all, just like a poll. How many of you here do data science? All right, I see nods. I see here I do. Yes. Okay, great. So how many of you here have heard of Rapids?
we got at least one, two.
No. Oh my goodness, this is great. All right. Tom says he has. Cheng, Winston, Winston, you have definitely heard of Rapids. So we're gonna have some fun today. This is gonna be, for my part of the presentation, it's gonna be a little bit more of a showcase as well as an explanation and an introduction to Rapids. Change. There we go. So this is also going to be a very interactive session where we're not just going to do live coding. You're going to be able to join along with us and start to play with Rapids on your own as we talk, and then kind of see it and experience it for yourself. So the first thing we're going to do that William is going to help us with is we're going to set up our fun space. We're going to actually set up and provision an instance with a GPU, just in case you don't have your own. And we're going to allow you to run Rapids and Blazing on BlazingSQL.com. And then, Will's going to walk us through setting that up. Then it's going to come back to me, and I'm going to kind of just go through Rapids and give you an overview of what it is and why and what problems it's trying to solve. We're going to do some live coding, and then I'm going to talk to you about how to join the community and what that community even looks like. And then we got some introductions of some great people. I don't know who they might be, but I think Jacob just introduced them pretty nicely himself. Throughout this exercise, we're going to have. You're going to be able to ask some questions, so ping me. I've set up my dual monitors so I can see a message in the Slack. And then we have Saloni from the Rapids team on here. Hey, she might be able to field some of those questions. There she is. As we talk, and then anything else, I'll try my best to answer as we go through. Okay. So without further ado, let's set up our fun space. There's 4 steps to this, and Will's going to kind of go through it, but obviously, take it away.
Yeah, so we're going to be doing some stuff with BlazingSQL notebooks, and if you go to BlazingSQL.com, you can click on Try Now, and it'll take you to app.blazingsql.com, or you can just go straight to this address. But if you have a Gmail account, a Google account, you can just click it, and you'll be able to go straight in. And it's completely free, and you'll end up with a Jupyter Lab instance. Anybody, I'm imagining that a lot of you guys are familiar with Jupyter. But basically, this is a Jupyter Lab instance with a GPU attached to it. And it kind of already comes preloaded with a whole bunch of introductory notebooks to both BlazingSQL and Rapids. Actually, later on in the talk, when I'm going to be actually just going over some of these live.
William, can you please increase the font size, make it a little bit
Oh,
bigger?
yes, absolutely, absolutely. Thank you for reminding me.
Yeah.
Is that better?
I think so. I can see it now.
Okay, great. But yeah, I mean, basically, BlazingSQL notebooks. It was kind of created to help people like really just play with Blazing and play with Rapids in like a Jupyter environment that they're kind of used to. So like you can create your own notebooks, have them in there. It's not really designed for you to load all your data science data into it. But with Blazing, you can, like if you have data like on S3 buckets or something like that, you can access it there. Really easy. But yeah, just we want to kind of welcome people to go try it out, and you can follow along with us. So that's BlazingSQL notebooks. Back to you, Taurean.
All right, taking back over. So I put in a chat window. This is for for those of us who are more advanced and would like to follow along to kind of join in on the fun. If you would like to just watch, you're more than welcome to. I'm going to have the notebooks also up on the screen, and we're going to run them. You should get 2. Jeff, you may need to refresh. Will, why don't you go through a little bit more on?
Yeah, if you get a 400 error or 500 error, you refresh once or twice, it should go back. Authorization state missing from cookies. If you have cookies blocked, it might not work. That might be potentially a problem there.
Uh-oh. All right, so Olivier got it, so that's good. All right, but I sent in a git clone line in the chat. If you scroll up to where I am, if you go to terminal as shown here and run that, you should be able to git clone a couple of notebooks that I prepared for you just to make it a little bit easier. And then when you get into those notebooks, hold on, let me actually alt-tab into some of these. So here's mine.
Can you post that GitHub link in the chat?
It is in the chat.
Oh, sorry.
I'll post it again.
Oh, no, I see it. Thank you.
Yeah. Okay. So the 2 we're going to use are Rapids decomposition and New Year's correlation. There's also this UMAP demo full, but in taxi years correlation, what I would suggest you do is that you start off with these 2 and you actually run them. This will allow you to download anything that's missing, especially while I'm talking. Okay, so then by the time we're there, you should be good to go. Okay. Alt-tab out. Oh, that's the wrong one.
Taurean, we gotta get you more onto this BlazingSQL. That way, you would just read the files straight from S3 without having to download them onto the box.
I know. Well, we're gonna definitely be talking about that in after this meetup, because this is gonna be a lot of fun. So yeah, please just download the data for at least the New York State one. That's a few gigs, and let's just get started on what is Rapids and why are we here. So, how many of you here are familiar with the Pi data stack? Pandas, scikit-learn, NetworkX. There you go. Terminal does appear for me. That's good. Awesome. So,
are you supposed to open the Python notebooks that you cloned?
Yes. So you.
And how do you get that to appear in the left side. Sorry.
Let me show you, just so we come through. Okay, so you see the folder icon? Sometimes when you click on it,
Okay, there we
it'll
go.
disappear.
Perfect.
Yeah, so you're gonna go to 8 p.m. July 2020. Made one just for you. Then you'll have some of these here. All right?
Perfect. Thank you.
Okie dokie. All right. So for those of you who don't know, the Python data stack allows you to do your data prep, ETL and stuff, as well as, and then go to training your model and then passing it along to whatever the rest of your workflow might be, whether it be a visualization, whether that's the end of your workflow, or if you have some deep learning that you want to do, then you could pass it on to PyTorch or TensorFlow, and continue on with your work. So usually for your data frame and just your manipulating the data itself, you use pandas for your analytics. Then there's scikit-learn that does the machine learning, and so basically you run your models using scikit-learn on that data frame that you did with pandas. And then you can scale that out with Dask if you'd like. So you have multi-node, multi-GPU, at least on the Python data stack, right? Then there's NetworkX for graph analytics. And how many of you are familiar with NetworkX itself? Craig is like, he's going to keep his hand up. It's going to be great. So, that allows you to do all your fun graph analytics. And you have also GeoPandas for spatial. I think it's scipy.signal for signal, and there's I don't recall the cybersecurity libraries, but that's on me. But now, what is Rapids? Well, Rapids is basically a set of libraries that tries to be API familiar, that instead of you importing pandas, you'd import like cuDF, and it will then allow you to do the GPU accelerate your data science workflow from end to end. So you would be able to bring in the data on cuDF, and then using Apache Arrow as our memory format and having it on GPU memory, you would keep the data there all the way through until you're done with your analytics. And we'll talk about in a second. We're going to talk about a little bit more on how that helps. But in a nutshell, what happened? Down. In a nutshell, we are open source, an open source set of API tools. We work with a community, and we have a community that contributes to us and we contribute back to. This whole thing is built on top of CUDA. So earlier today, we were talking about how CUDA allows is allowing us to use GPUs as a general purpose compute capability, general purpose compute. So what Rapids does is it adds these layers of abstraction on top of the CUDA library, so you don't have to do things like memory management or having to declare how many processors you have or which cards you're going to. Rapids takes care of all of that, and it does that while remaining to have a familiar API. So you don't have to learn anything really new. You just have to be like, oh, well, let's see how that looks, right? So this is your actual this is a scikit-learn and pandas clustering workflow, right? We start with pandas, and then we go to scikit-learn and run dbScan on it. And this is how hard it is to launch Rapids. I know you're gonna it's a crazy changeover, but yeah, here it is. You just literally switch out pandas for cuDF and scikit-learn for QML, and everything else works great. So we'll do it again for those of you who missed it. That is your CPU workflow, and now here is your GPU accelerated workflow. And like I said, we are open source for the win. We do contribute back. We have companies who contribute with us. You can contribute too, and we'll talk more about that later. But also, we love to contribute back to the open source community. And in some cases, it's a very nice cycle of love that we have here, and what we kindly call ourselves in the Rapids ecosystem. So now that you know, kind of like at a high level, what is Rapids? Let's dive into why Rapids. And the reason why Rapids is because we've had a big problem with big data. As you know or may know, there's more and more, our data sets are getting bigger. There is more and our models are getting bigger, and we have to process them still. And Moore's law for CPUs, you probably heard this before, but Moore's law is slowing down for CPUs. But with GPUs, we're still going strong. And we're hitting 20 teraflops in some of our larger GPU workstations, which is basically like having a supercomputer on your desk. And that really allows you to not do this. We have this trade-off problem we do where we basically are like, hey, listen, instead of running for days or months in some workflows, we take less of the data, and now we're trading in accuracy for that. So how do you solve that? And we came, because iteration is the way to win at data science. For us, it's Rapids. You use Rapids. And how does this work? Well, let's take you through a journey of history, right? We'll walk down memory lane. Some of you may know about things like Hadoop and Spark. You remember these guys? So, a while back, I remember when Hadoop started becoming huge, right? Like you're like, oh my goodness, we can scale out and have like all these large clusters. And this allowed us to improve how fast and how big of the data set we can actually process in a reasonable amount of time. And that was great. And but still there was room for improvement. So we had Spark, and Spark said, hey, listen, let's take all these HDFS reads and HDFS writes, and let's just put it all in memory. So now we just query, we do our ETL and we train, but we only read once. And that was going well up until we started reaching compute bottlenecks. And I don't know how many of you how many of you have experienced any compute bottlenecks? Oh, there's the hands, right? Greg didn't put his up this time, but that's okay. He's like, no, bro, you don't understand what I work with. Got it. So what became interesting was, I think Go AI, we started to realize, after we started to figure out how to parallelize our normally serial models, and then start to use GPUs to actually do some data science workloads. And what that led to was a kind of happiness for some of our data scientists who actually used it. You would be able to iterate faster. If you had a problem, you would be able to fix it quickly. If you wanted to add a feature, you'd be able to do it, and you'd be able to go home on time, which is wonderful for some of us who aren't workaholics or are workaholics but want to do more with their day, right? But then we decided, let's just go back to this. But then this was also a bit of code glue, right? So you have pandas and scikit-learn. You have to read your pandas data frame. You have to hope that you can pull that data frame in with scikit-learn. There's some GPU and CPU reads and writes here, similar to that workflow that you normally have. Then you have your ETL. So we're like, what can we do to speed that up? Because that ended up being our bottleneck, just reading and writing from GPU memory to CPU memory and back again. So we started, like I said, using the Apache Arrow format, and we just got rid of the conversion in between. So now, similar to Spark and doing in-memory process, we read once to Arrow, which is a format that almost every capability everybody in the PyData stack can read. And then we run our query in our ETL, and that gives us a massive speed up. Okay, like, and we're able to now, it's kind of fun to say this. We start doing workloads because we can. And in fact, one of those workloads in that notebook is one of those because we can kind of workloads. And we'll go through that in a second. So actually, we'll go through that now. I forgot to make the list. Mike's going to be so mad. Poor Greg. All right, hold on. There we go. Okay, so let's start with rapids decomposition.
I think you're all the way at the bottom.
Yeah, I usually am. I'm going to restart the kernel. Yeah, just to make this thing. So this is, and like I said, we are doing a showcase, and Will is going to come in and do more of an introductory tutorial on the demos. I'm just showing you what is a little bit of what's possible on a single GPU. And then I'm also going to show you on a workstation, and this is on Blazing for now. And then on a workstation, I'm going to show you what happens when you have either a GPU on a provisioned cluster or a GPU in the room over. That's really nice. And just remember, you can run these on anything 1080 or newer if you're doing consumer grade, and T4s, P4s, or newer if you're doing workstation grade. So no K80s, which you'll sometimes get. But if you've ever seen this, this is basically a test of decomposition methods, right? It's a benchmark for decomposition methods. The link is here if you want to see the real one and actually go through it. For time's sake, we will not do the real the CPU version, but we're going to import our libraries, and I'm just going to run everything right now. Which I probably shouldn't have done, but basically we're going to do TSVD, PCA, and UMAP. I think we're done. Yeah, we're done. Okay, so what it's done is we've actually run 5,000 samples and 10,000 samples on TSVD, PCA, and UMAP, and we've done it twice for these for both full and just Jacobi, and you now have your outputs, and it's 0.63 seconds. I think the largest one is going to be yeah, it's always UMAP that takes a little bit of time. But to put this, I'm going to put this in perspective, and I left you the link so you can bring it into Blazing, and then you can actually run in the CPU version itself. But when I ran this on, I was a galvanized SF, and I was just teaching a class. I ran this for them, and in a collab in another window, I had it running. I had the CPU version running. It took about 7 minutes. And one of the interesting things that I highlighted later, and I'll actually do it right now. And I'd also truncated like what it was, so it'd be an apples to apples comparison. Let's open this up in a new window. They're only doing 500 and 1,000. We're doing 10 times the size, and you'll get like about 7 to 10 times the speed up. So this is kind of what you'll notice with rapids, is that as your data set gets bigger, you'll start to realize kind of like what's going on, like that your speedups get more and more. And I'll actually do this in here. So this is, I actually just, while we were talking, I just kind of I kind of created this. In fact, I meant to make this markdown. No, all right, I'll fix it later. But we're gonna bring in, let's restart this kernel. And this is a pretty simple example, because cuDF, when you're working with data sets, you kind of do it on, people, we use strings in our data, but strings are generally considered hard for parallel systems to work on, right? So what we're going to do is we're just going to come in, and I'm going to kind of show you it, and something that you'll find out with rapids is that when you bring it in, we're going to time everything. It's pretty much same as the pandas, right? We just switch PD, pandas, and cuDF, right? But you'll notice that the read times for pandas was a lot quicker than cuDF. And you'll be like, what's going on? And that's because we're really just working on 4 different elements here. You know, it's not even enough. The latency in actually sending that data over to this GPU is higher than it would be to run on Pandas. So there are obviously like there's levels that you would want to be like, okay, yes, PyData, you know, we'll use the standard CPU PyData stack, but then, you know, pretty quickly it'll take some time for you to actually run it on your standard CPU workload. And then that latency in transferring the data over to GPU memory stops being much of a problem. So let's take that same 4-character string, 4-element string, and let's multiply it by 10,000. 10 million, sorry, not 10,000, 10 million. And let's look at it again. So one of the cool things is that the GPU, you know, this isn't even enough to fully saturate. Sometimes we get up to 15 times as fast to read on Pandas. So I've had like 30-minute Panda read on just the data, read CSVs that take 2 minutes on cuDF read CSV. In fact, like we were doing a Kaggle and I kept on telling him, use cuDF, stop it. And he's like, yeah, but it takes so long to do it on Pandas. Like, I didn't understand why he wasn't getting in there as fast. And he's like, oh, I'm using Pandas. I'm like, use cuDF. He did it, and like a couple minutes later, he's done. So first, you know, we accelerate the read times as faster. But here we're going to do, and we've already finished the 40 million rows, 40 million elements, and we've sliced it and removed the character, the first character here, and then converted them to int. And here you're going to have fun with Pandas. So all it's done is just done the first print, and then we wait. Now this is, and that takes 18 seconds. Now this is this is a workstation. It's an HPZ, I think a Z38. So it's got dual Xeons in it. And what you saw there was just one GPU working on this, on our cuDF. So as you can see, very similar API, able to work on strings, and we work faster on numerics. But you know, you're able to immediately see, speedups really quickly once your data goes to scale. So let's go to, let's come back to here. So this is one. By the way, do you have any questions? Anyone have questions? I can't. Yeah, gestures wildly.
I have one. If it's okay to ask now, you're using a bunch of library. You're basically replacing the libraries like the Pandas library with your cuDF. You
Yep.
also do this for scikit-learn, correct? Or
yep.
Good. So
we're gonna get to that too.
Okay. So do you support all the functionality that are like in Pandas, or is there some functions that you don't support?
So there are functions that we don't support. We do not have 100% coverage, and that's mainly because Rapids is just under 2 years old. Okay. Like we're in version 0.14, about to release 0.15 in a couple of great weeks, and that's to tell you the pace of our development, that we're able to come through and say, hey, listen, like, you know, have major, you know, well, there's a slide down there where major companies are starting to use us, but Walmart has a blog where it's like from, I think it was like 2 days to 20 seconds, because we've come to the point where we've come to the point since like 0.4 or 5 where we're really starting to like be on our own and be something that is incredibly useful. And now we're at 0.15, so we're cruising along right now, and just adding more and more functionality. I do have in the appendix of the deck like the types of algorithms that you can use for things like cuGraph, cuSignal, cuSpatial, and cuML. And if anyone's interested in seeing that later, I'll be more than happy to show you. All right. So this one is a geospatials. How many of you here have worked with geospatial data before? Okay. So I'm not seeing too many people saying yes. It has been my privilege to work on this in QSpatial, because when we started doing the CPU version of this, and you'll see it in here when I start doing it, when I start doing a similar version there, it is long. It takes a long time. Especially for the kinds of data that we're about to consume and process. So how many of you have heard of the New York State taxi data set? Like it's a pretty popular data set for trying to do things like linear regressions or doing clustering or finding patterns or even XG boosting. Well, basically, New York City taxi data set. New York City actually keeps track of all the rides that happen. They have, and we're just going to look at it right now. I already ran that. Let's come to here. So, and this one you can run along with. So I'm actually going to put this in here. Each one of these data sets is about 2 to 4 gigs, I think it is. Taxi. It's interesting. It's still reading. It should have stopped by now. Yeah, let me stop this. Hold on. Oh, we just ran out of memory. My apologies. I need to shut down some stuff.
It might be that we have maybe 20 people trying to do the exact same thing on the same GPU.
Yeah, I was like, that's never happened before. All right, this is also our first, at least my first time using Blazing with a group, and this is going to be a fun learning experience for all of us. But yeah, like you have your dates and times that you're picked up. You have your passenger counts, trip distance, the longitude and latitudes, and the drop-off points, longitude and latitudes. But in 2017, they changed it. And I'm gonna have to shut down. I could probably run this in mine. Is anyone else getting CUDA any memory allocation errors? Just kind of curious, because then if you're not, then I'm gonna switch over to my main machine. Just type or say.
Yeah, there's a couple of people. Some people have gotten a crash, some have not.
Okay. All right. So then what I'm going to do is I'm going to keep it moving along onto the next one, and then I'm going to wget it and bring it into here. So let me just do that. I should have used, I'm sorry. So let's run this. Let's run this, and then I'll wget it, and then you can probably run it on your own, but let me just walk you through what it actually does. So what happened in 2017 is that people were like, yo, we're getting all these amazing latitude and latitude and longitude points, and we can't, it's taking a long time for us to take your boundary file of New York City and the 5 boroughs of New York City. By the way, I used to live there, and actually make some decent sense of it in terms of spatial analytics. So what they did was they decided to move to another format, which was using these things called location IDs. And what those location IDs did was that they broke down all those longitude and latitudes and just put them into 265 different locations, in the map, basically polygons in the map, and you're able, see, that was a lot better, how do we have it? So then, your 2016 had, now we'll do 2017, and you'll notice that now, instead of having it, it has pickup location and pickup ID. And that's all well and good because now we can do processing, but now you can't correlate any data between anything pre-2017 and post-2017. So this notebook is actually probably one of the first reasonable ways that you can actually do that. So what we're going to do is we're going to set the columns, and we're going to now import our stuff from GeoPandas into QSpatial, our spatial data into QSpatial. And now what we're going to do is we've got 10.7 million. Did we only do drop-off locations? Or we did? Yeah, we did pick up locations too. Yeah, I'll have to change that. 10.09 million drop-off locations and pickup locations across 263 different polygons, across these rings, across 98K location coordinates. And this is going to take a little bit of time to do it on the shared GPU, but while we wait, but it's not going to be the insanity that would have taken for you to do CPU. So while we wait for that to go, we're going to run on an actual machine with an actual GPU on it. I'm going to restart the kernel as always, just so you can see it. So this one we couldn't do, and there's a reason why we couldn't do this one on here, and I'm going to show it to you right after the other one is done, because we did talk about several different ways. So, and that is the fact that we're going to use cross filter. And we talked about that visualization layer that Rapids has. Look, Greg's smiling. I'm going to use Greg. He's got those expressions. And we're going to look at how quickly we can kind of do some of this. So we're going to actually now do 2015, which has a little bit more, a bit more rides. We talk about how you can, in here we talk about like this is how you can, this is what the cross filter, not cross filter, the QSpatial data frame looks like. We show you how to pull this out, and we show you how to work with polygons in, for in case you needed to do something very special. And that's actually how we did the other one. We played with the polygons a little bit. And then we're going to
asks if there's some significant reason for 263 separate polygons of New York City.
That is basically, it has to do with how New York breaks apart its boundaries. They're actually named, each one of them, and also to keep some of the data in. That's my best understanding. If there's somebody else who in the future will come in and comment and be like, no, you're wrong, then great, please update me and forgive me for my ignorance. But what we just did is we just took, and I skipped over it while I was listening, we just took 25 million points, because it's 12.7 million pickup features across, the actual boundary of New York City, which is a different boundary map than the one that is in the other one. And we actually did all of them in 7 seconds on a GV100, a single GPU. And I've got and it's kind of interesting, depending on how your GPU is configured. Like, remember we were talking about architectures and the GPUs. Some of them have more floating point 64, a better flops, and some of them have, or they're optimized more for float 32. This one is, when you have something that's really optimized for float 64, like the ones that my friends have, they actually are able to get this done in 3 seconds. Now, to put this in any sort of terms that is imaginable, that is, we kind of talked about, I'm not going to run the CPU. It just takes too long. But this takes minutes just to run. This example, what we had to do was first pull out only a few rings that you're even looking at, and then remove, and then iterate over the first like a random 1 million. So 1/25 of the data size across like what it looks like I think it's like 25 of the 7,000 ring. Sorry, of the 25 of the 107 polygons, and of these borough coordinates, and it will take, about 7 minutes to, some minutes to do on certain GPUs, and the speed up ends up being, well over 1,000. So, take our 3 or 7 seconds and multiply it by 1,000, and that's how long you're going to be sitting there for. In the interim, what we're going to do now is we're going to take this data that we did, and then what we're going to do is we're going to clean this data. And I'm going to show you why in a second. So we started doing like pickup boroughs and inner boroughs so that we can kind of like have some fun. And in this line and this line alone, what we've done is we've now isolated all the taxi points that happen that are all over the map, if you will, where taxis can pick up and drop off in the near tri-state area, and then isolated them to just the 5 boroughs of interest.
So, hey, Taurean, sorry to interrupt, but how much longer?
I'm almost done.
All right, thanks.
All right, man. All right, so I'm gonna speed up because that's my cue to skidoo. We're gonna go back to here. Yeah, this is still running. I was trying to like burn time while this ran because this one does take 5 minutes. But the dashboard is running, and what you're gonna see here is this, and this is the last demo, man. Don't worry, I got you. This is kind of cool about cuSpatial, and this is the so what of one of my favorite so whats of cuSpatial. So here we have 27 million points up here in pickups, 27 million points in drop-offs. You can zoom in, and now you're starting to see how dirty the actual the data was. Give it a second. So you see, like, there are points in the middle of the of the bay, and that's kind of like, that's probably where like the mob drops off its their victims. But what you're able to do is you're now able to clean that out by highlighting, and actually doing some cross filtering. So you'll see the points here disappear. You can just select the points from Manhattan. Sorry, there's a little bit of a delay, but it is working with like a massive amount of data. But the cool thing is, after you're done now understanding and visualizing what it is that you're doing, when you come back to it all and you run this export, what you're able to do is actually create a whole new data frame from what you've selected on the other side. So you see we've selected the boroughs here, all 5 boroughs here, and we removed all the extra points that were outside of the boroughs. And what we can then do is, in this new data frame, which is called cuX clean, which is cucross filter clean. And then what we're going to do is compare the data. And then finally, what we're going to do is we're going to see the differences between those data. Let me see here. All right. So for sake of time, oh, good. This finished off. And we're able to, okay, they killed it. Oh, well, that's live demos, but at least you actually have the notebooks, and you can actually play with it yourself when there's not as much traffic on the actual cluster. But what ended up happening is that now your 2016 and your 2017 data is now correlated. You can now do like your Holt Winters or your REMA to start doing your time series, and now your data is back to being unified. All right, let's just go back. So what Rapids is trying to do is, CUDA has become a foundational layer for machine learning and data science. We're also trying to become, we're also trying to become a foundational layer of data science, and fill that niche, similar to what CUDA, like built on top of CUDA, but similar to what CUDA did for deep learning. We're working with cloud vendors, with downstream in your workflows, and then with other community members like in the open source community like Plotly and Datashader to really flesh out a full experience for you in Rapids, right? And there's some really cool stuff that's coming out next week with Plotly, and you're going to see just how you can take Plotly and create web apps out of Rapids, because now what you can do in hours now takes seconds. It's going to be really fun. We have our ecosystem partners. You've seen half of this before. We have adopters in, these are some of the companies that use us and swear by us. And then, of course, there are people who kindly build on top of us, like Envy Tabular for recommending systems, a company called Streams for doing stream processing, and then, of course, I don't know these middle people.
BlazingSQL.
Oh, somebody knows it. Started with, this is also in our community links. We have Rapids, then build your own workflows, join our conversations, and contribute back. We'll walk into that in a second. So we have on our website, rapids.ai, that we have the ability, you have this quick way of figuring out what your install command will be, and it's updated with every release. You have nightlies and stable releases, and you're able to select what you want. We also have Docker containers. Our GitHub, you're able to contribute, see, and edit the code. It is free and open source. Have fun. We have docs.rapids.ai, so you can read our docs and see where, what features you're looking for and how to implement them. It should be similar to Pandas. Every now and then there's, a slight difference, but, it's just the way, because we're working on parallel systems. We have blogs out there to help you go through and understand a little bit, different features or capabilities, or even just show off what you can really accomplish. And then there's notebook tutorials. There's notebooks proper. There's notebooks in Trib, which is going to be moving to become more community driven soon. And then there's tutorials, and Blazing has a few great initiatives going forth. And then, of course, you can join the conversation on Google Groups, on Slack, or go on Stack Overflow. We are very responsive, and we try to be, and get you going on your workflows. Every now and then you'll see Josh, who heads our engineering. He's our senior director, or Keith, or others, and myself will actually chime in. It's a full community effort. So with that, I want to thank you for your time. Keep playing with the notebooks and enjoying yourself on app.blazing, and let's go on to Blazing Glory.
Yeah. First of all, I would like everyone to unmute yourself and give Taurean a big clap until we get the outro.
Thank you.
Okay, this is a nice one. Taurean, thank you very much. We do if someone has one very important question, please ask it. Otherwise, since it was a long presentation, we're going to skip directly to William with BlazingSQL. But first, anyone has any question that is pressing? I saw several questions being asked. We didn't want to interrupt that much, but anyone wants to repeat the question or ask a new one? No questions? What's the ring?
No new questions. I did a good job.
Yeah, you did a good job. That's for sure.
Sorry.
Well,
Yeah, I know we had 25 to 30 minutes, so I tried to hit that. But,
Yeah. Well, actually,
I do have a question, but I think it might be too big for right now. I don't really understand why GPUs are so much more computationally effective than traditional CPUs, but I feel like that's kind of a big question.
I'll be more than happy to chat with you on that one. But it basically is how we process the data. We have slower processors in terms of speed, but we have more of them. So it's kind of like having a single person doing like working on a car, single person picking up bricks, right?
Mm-hmm.
If there might be the best brick picker upper person there is, but and move really fast. But you know, if you have like 10 people doing it, they'll after a while they'll you know, the more people you add on that on the brick pick up and move, the faster that job will get done.
I too would like to talk about that if anybody if you're all interested in staying around later.
Awesome.
Okay, so Taurean, let's stay for later. We're gonna talk after we finish the other talk. We're gonna stick around, and people usually talk for a few more minutes afterwards, if not an hour or two. It happened before, but at that point we're not recording. But for now, again, I want to thank you, and please unmute yourself. Give a clap for Taurean.
Thank you, Taurean.
Thanks, everyone.
Yeah. And Michael will want to stay until the end, but William will take over now, and he's going to show us how BlazingSQL works. And so, William, take over, please.
All right, thank you, Jacob. Thank you, Taurean. So,
all yours.
My name is William Malpica, and I'm the VP of Engineering and one of the co-founders of BlazingSQL. And basically what we're trying to do with BlazingSQL is just make it like really easy for like data scientists and data engineers to seamlessly scale their Python and their workflows to terabytes, make it really, really, really fast. And just like Rapids, you know, we're part of the Rapids ecosystem, and just like Rapids, we're fully open source, super GPU accelerated, and we, you know, kind of like how Rapids is trying to, you know, make it following similar APIs that data scientists are already used to. Well, we're doing SQL, which is what you know, the most well-known language for data analytics that there is. So this is a slide very similar to what you saw with Taurean, but basically this is kind of how we fit into the Rapids ecosystem. You know, BlazingSQL is another library, another package, much like cuDF and cuML and cuGraph, that it can scale, and you can kind of schedule it. You can scale it out across to multiple servers, multiple clusters using Dask. And then it also uses this GPU memory, like based off of Apache Arrow, like the same memory layout as the rest of the Rapids ecosystem. In fact, most of the compute primitives of BlazingSQL are the same ones as from cuDF. And what that allows, I think Taurean alluded to this, is that it makes it really easy to interoperate between the whole ecosystem. You can like pass data frames from one library to the other without having to copy or serialize or do anything like that, which kind of lowers your memory footprint because you're not having to make any copies, and it just kind of makes it also that much faster. So, but now to, you know, I kind of like just kind of diving straight into it and explaining, and I kind of wanted to show more hands-on approach to Blazing. And well, you guys kind of already all know how to use an app at app.blazingsql.com. And there, when you first go in, it's already preloaded with a whole bunch of notebooks. So I'm going to be diving in and kind of showing, just walking through some of those, because I feel like those really explain Blazing's capabilities and how simple it is really well. The one that I'm going to be looking at is the data frame notebook, which a lot of the examples, a lot of the stuff that I'm going to be looking at here are going to be touching a lot less data, because it's mostly for the purposes of just showing the APIs and how simple it is and what you can do with it. So feel free to jump along. We should not be having any out of memory errors. We're not going to be loading up lots and lots of gigabytes, at least for most of the demos anyways. So BlazingSQL is, it's not a database management system. It's not a database. It's a SQL engine. So one of the things that entails is that it's not it's not a stateful thing. You don't ingest data to it. All the statefulness that it has is due to its context. So basically, if you import from BlazingSQL a BlazingSQL context, you can then create a BlazingSQL context, and that is all you need to do. Oh, that took a while. Yeah. I guess there's a lot of people on here now. Now that we have a BlazingSQL context, there's two main things that you usually do with this. You create tables and you run SQL. And that's like the bread and butter of any analyst that's using SQL. So first, we already kind of saw a little bit of QDF, similar to pandas. I'm just going to read a taxi data set. This is a smaller version. It's not like a full year or anything like that. But you can see that the output, my read CSV, is a data frame, and I'm going to just create a table. I created the table off of this data frame, and when I'm doing this, it's not creating a copy of this data frame. It's just picking up a reference to it. So I'm not duplicating data or anything like that. I'm not having to ingest it or do any indexing or anything like that. Blazing never really does any indexing. It just runs on the raw data frames as they are. But once I've created my table, then I can just run a SQL query straight up. And you can see that the output of this SQL query is a QDF data frame as well. So just like everything else. And it's as simple as that. Now you can also query files directly. So here I'm kind of using the exact same file, but this time instead of creating a table off of a data frame, I can just create a table from the file. And again, when I create this table, it's not reading this file right now. It's actually just like being like, oh, okay, the file is, this table is this file. And for CSV files, you can have a whole bunch of other parameters like what the delimiter is, whether to ignore the header or not. If you want to be very explicit with the data types, you can do that. In this particular case, Blazing is smart enough to infer what all the different data types are. And it's only really when you actually go run the SQL query that it actually reads the entire file as needed. To be able to execute the query. And I'm assuming that everybody is running this because I'm usually does not take this long. It only happens with a live demo, right? So by show of hands, while we're waiting here, by show of hands, who's running these demos with me? Our commentary. The rule of demos. That is weird.
It seems we need to get a bigger demo machine for the next demo.
Yeah, we'll spin up a couple so that the everybody's like on different machines. Yeah, let me just restart the kernel and do this real quick again. So either way, there's lots of, with Blazing, like you can create tables from all sorts of stuff. And actually, so that if you guys ever are trying to figure out, oh, how do I do this with Blazing? I'll direct you again to our website. And here on the top left, there's this docs link. Now, if you go to our official documentation, then obviously here we have all the information about all the different things that you can do. So, for example, I can see how all the different types of tables you can create, whether it's org, parquet, off of data frames, or QDF DAS data frames. You can create tables from pandas, text files. You can even hook it up to Apache Hive. You can kind of give it a Hive cursor, and then it can like pick up the locations of all your files and stuff like that. So it can be really convenient for that sort of stuff. And again, this is really stalling out. Oh, this is a first for me, ladies and gentlemen.
We wanted to workstation. This one's not behind a VPN. It's actually in on the other side, and I can give you a link to keep running?
Certainly.
All right, let me start with that, and then I'll Slack you the link. Give me 1 second.
Tom, can I interest you in a load testing service? I'm putting together service. You know, I just might reach out to you about that. In the meantime, while we get that link, I also wanted to point out that you can connect Blazing to S3 buckets or other different file systems. And so basically what you can do is that you can register a file system with Blazing. You can tell like, hey, here's an S3 bucket. In this particular case, it's a public bucket. This is kind of all the information that I need to tell it. If it's a private bucket with encryption keys or connection keys, there's a couple more parameters. But then you can actually query data that's directly in S3. You can query data directly in an HDFS file system on Azure Blob Store. Actually, Azure Blob Store will be coming soon. Google Storage, Min.io. So we have several of these storage plugins that you can kind of leverage as well. So you can kind of query your data wherever their data resides. And here we go. Okay. Well, we have my context. Let's try that again. Let's register an S3 file system. And I can create a table now off of, in this case, I'm doing a Parquet table from my S3 bucket. And you can query it just like anything else. Now, we talked a little bit about, I guess Taurean talked a little bit about QDF.
And someone asked to increase the font size a little bit more, if it's possible.
A little bit more? I sure can. Is that better?
Yeah.
And actually, I think, and this one also need to increase the font size. There we go. So when we're talking about the different, mentioning the different storage plugins again, we currently support AWS S3, Min.io, Google Storage, and HDFS. There we go. And we are certainly saturating the system today.
Yeah. Sorry, we're trying to conda install right now.
Now let me try something real quick. I'm actually going to, let's do this. It's remembering my old user. Actually, let me try. I apologize, everybody. This, as we saw earlier, it was all working just a second ago. But anyways, one of the, as I was saying, so for QDF, you know, it works just like pandas, and it's we kind of it works just like pandas, and you can easily create columns. Here we have like creating a data frame. But what's cool is that you can interchange using something with a pandas-like API with QDF and SQL and back and forth, given that the output of a SQL query is just going to give you a data frame, and then you can quickly then go do QDF stuff with it or pandas-like stuff with it and back and forth, which makes it very useful because there's some certain things that is very easy to do with pandas-like API that are just manipulating a data frame, and some things that are really, really straightforward to express using SQL. And similarly, if you want to do something with machine learning, so now here I've switched over to the machine learning notebook. You can also interchange, back and forth between Blazing and QML. For example, you could, create your Blazing context, register your S3 file system, go create a table from S3, and then you can, load QML. So we're going to do like some machine learning, a very simple linear regression example, and you can basically get your X and Y, your what do you call it? What you're training and what you're testing. You can do a split, do your linear regression, and you're basically doing your ETL with SQL, and then your machine learning with QML, and all while maintaining the data in memory, which would kind of help you streamline your entire process. Kind of going back to what Taurean was talking about, being able to do multiple different iterations. You can do your ETL, change a couple parameters, test a slightly different model, and over and over and over again to kind of speed that up. But now I kind of want to show you a little bit about, if we want to do at a bigger scale, if you want to do larger and larger, then you need to build out a cluster, right? And so if we look here at our documentation, you can figure out how do you do it with multiple GPUs. If you have multiple GPUs or multiple servers, you can also scale out Blazing, and it's actually really straightforward. If you have just a single, by the way, is this font size good enough?
Show us again.
All right, I think it's good. So if you have just one single server with multiple GPUs, there's this function called local CUDA cluster, which is available from Dask CUDA. And that kind of gives you a representation of your cluster. And then you can create a Dask client, and then you can feed that Dask client to our Blazing context with this Dask client parameter. And once you have this, then all of a sudden you have a distributed BlazingSQL cluster. And when you run queries in a distributed context, it's exactly the same, except that now you have a Dask cuDF as opposed to just a regular cuDF. Now, a quick show of hands. Who here has played with Dask? The Dask is like one of the ways of distributing with Python. So I'm hoping to see a lot of hands. But basically, in the Dask cuDF world, it's the same concept. You still have like a pandas like data frame. It's still a data frame, except that the rows are kind of distributed across your multiple different GPUs. And you can kind of materialize it all into one location by doing like .compute, and you can then see it there. But ultimately, you can do a lot of the exact same operations that you would do, just with the slightly different syntax in terms of, because then you're kind of like submitting jobs and doing stuff like that. And that same concept, that is the output and the memory representation for Blazing when you're working in a distributed context. Now, if you have multiple nodes and multiple GPUs, then you will have to launch the Dask scheduler yourself and launch the Dask workers yourself on different servers. And then you can create a client, again, just by passing it the IP address and port of the Dask scheduler. And then, once again, you're good to go. All of a sudden, you can hook up, 100 GPUs, 100 servers, if you want to have if you have really big problems. You can run it out.
Will, I sent you the link.
All right. You sent it me via Slack?
Yeah, on Slack. Punched a hole through my router. Be gentle.
All right. Let me
My
check.
firewall on my router, sorry. And shared it with everybody.
All right. Look at that.
Make it big.
All right, so yeah, you should have Blazing context installed right now, and you're just gonna have to import your notebooks. Do a wget.
Yeah, although actually what I can do real quick is here, let me
Create a new folder. Yeah.
zoom in real quick. So I kind of wanted to just show this guy off real quick. There we go. We're back in business.
Yeah. Next time I'll use a DNS mask. Hey Jacob, do you mind blurring that out later on? I kind of like that name. Don't want to lose it because I let it out.
You lost me. What did you ask for?
My DNS.
It's not. I don't see it on my screen. I don't look at your chats.
No. It's on the. It's. He understands. It's all over Twitter. Thanks a lot, Greg. It was a good 5 years while it lasted.
We can later mask something in the recording if you need anything. Stay online after the recording. We'll figure it out.
Don't worry. Don't say I don't love you, Will.
Thanks, Taurean. Yeah, so like as we can see here, you know, like it makes it really easy if you can just kind of hook up with S3, which actually this is what I was telling Taurean, is like, hey, you know, you didn't have to wget all these files back into your local system. You can just query your files directly wherever they reside, you know. And not only that, but what's really cool about this is that you can have data on Google and data on S3 and then in your local system and in HDFS, and you can do a table join with data across all these different storage systems. And which is really cool. Like you can have just data anywhere and you can query it really, really, really fast, which, speaking of fast, I kind of wanted to showcase a couple benchmarks here as well. So we did these benchmarks, and actually these are benchmarks from TPC. TPC is like this big, you know, international. I don't know if it's international, but it's an unbiased, non-affiliated organization that they benchmark all sorts of data analytics tools, databases, database engines, and stuff like that. They have lots of different benchmarks, whether it's for transactional data, for just regular analytics databases. This one in particular is the big data benchmark. So it's the one that's done like for stuff like Hive and Spark and Hadoop. So for not only just SQL and ETL, but also machine learning and stuff like that. And at the 1 terabyte scale, the current, you know, best in class, the one that has the best numbers is Huawei with an Apache Hadoop cluster that costs a little over $250,000, and with, you know, BlazingSQL and Rapids with just one single DGX server with 8 V100 GPUs, which costs way less than half, we're on average running about 40 times faster. So this is like, you know, loading from disk, like doing the ETL and the machine learning for some of these queries that have machine learning workloads. And some of these are like, you know, sentiment analysis, or like also stuff with strings and stuff like that GPUs aren't necessarily known to be the best for, but the performance is insane. Which, by the way, this is at a log scale. This is just because at a linear scale the charts look kind of funny, but and these bars. So there's 30 queries here. We just selected our 2 worst, our 2 best, and kind of one in the middle, just so you kind of get an idea. You know, we're not picking and choosing where we did. We didn't even particularly tune the queries or the system or the parameters. We just kind of ran it. And this is like the sort of performance that we're getting, which I'm totally blown away. Like, I'm so impressed by everything that Rapids has done in terms of like the performance of these algorithms at this scale. Not only that, but we did it also at the 10 terabyte scale, where here the number one, of these benchmarks is Dell with their Hortonworks platform, a $1.2 million cluster. We did it with a single DGX2 server, which has, I think, 16 V100s. Sorry, this slide has a typo here. And this one, we're only running 22 of the 30 workloads. For some of them, we inevitably run out of memory at 10 terabytes. But we're still, over twice as cheap, and we're still averaging at 17 times faster over all of these different queries, which I think it's absolutely fantastic. And I think in general, like, these are the sort of like speeds that we're seeing throughout the entire Rapids ecosystem. Why this whole like being able to iterate and just being able to do more. You can do so much more with even less hardware and infrastructure. So again, we're also, just like the rest of Rapids, we're part of the where we're open source. You can kind of see all of our stuff that we're doing at GitHub at BlazingDB. We used to be called BlazingDB. We're now BlazingSQL because we realized we're just a SQL engine. We're not doing a database anymore. We have our Twitter and our blog. We're also starting up this Rapids Academy to have lots of webinars for tutorials and learning how to do data science there. I'd actually like to point out a little bit something else here as well. If you go to our GitHub repo, you can also submit issues and kind of help improve our engine, or you can contribute as well. But it also has some of our getting started. If you don't want to do BlazingSQL notebooks and you kind of want to do it on your own, you can install using Conda. We have a stable version which gets updated about every 2 months or so, and a nightly version that gets updated much frequently, probably every night. Or you also have instructions here on to be able to build from source. And if you want to get started, like I mentioned, Anaconda, BlazingSQL notebooks. We also have an offering on the AWS Marketplace where you can kind of launch your own private cluster, as many GPUs as you want. And that is me. If you guys have any other questions, I apologize for the technical challenges with the notebooks, but once we have a little bit less load, you guys can kind of jump in here and try them out for yourself. And I highly encourage you to do it. It makes it really easy not to have to worry about the infrastructure when you're just kind of trying out a new technology and a new platform. So yeah, that's it. You guys completely open for questions?
Yeah, first of all, we want to thank you, and please clap and make some noise. I see. Okay, good. So, thank you, William. Please open up questions. I have a question. What's your current like are there things that you still didn't do and you're about to do in the next few versions that you can tell, like things that you're going to make even faster that are currently still slow or something like that?
So a couple things that I'm looking at. We're going to be doing support for Azure Blob Store relatively soon. Windowed functions is one of the bigger SQL completeness components that we still have yet to do. Inequality joins we'll be doing soon. Those are like some of the biggest stuff. Like we're improving more and more our ability to do what we call bigger than GPU processing. So actually our ability to do bigger than GPU processing is really only about a month old, and we're still adding more and more features to be able to enable that. We're also going to be improving on our ability to do data skipping. So right now, when you query data, when you create a table from like Parquet files, for example, Parquet files have metadata that tell you the minimum and maximum of different values for different row groups. And we use that metadata to not to figure out what data we don't have to read, So depending on what predicates you have, what you have in a where clause, then we just won't read certain files or parts of certain files. So we're going to be improving that system for ORC, and then also for so we can kind of figure out what part, like if you have joins, we can be able to figure out what partitions don't join to each other. And so if you have like an inner join and we're like, oh, this partition, you're not filtering in your where clause, but it's never going to join to this thing, then we just won't bother loading it at all. So like those are some couple of neat little things that we're going to be doing. Oh, and I forgot the biggest one. We're going to be adding in support for UCX, which will enable taking advantage of certain technologies like NVLink, RDMA, and InfiniBand. So if you're doing like definitely more enterprise grade hardware and bigger clusters, that should make like a dramatic improvement in performance, because we'll be able to take advantage of much higher bandwidth interconnect between servers and interconnects between different GPUs on the same server and stuff like that. So
Yeah,
massive performance improvements with that coming real soon, actually.
yeah, I was just about to mention that, and then just put it in this chat to Sherry Chow's question about the largest size. Like the UCX plus Dask is absolutely incredible, and what we did with Blazing's help on TPC XBB, that's the scale we're able to accomplish, and then some.
Yeah, and after, we kind of feel like we blew TPC XBB out of the water, and after that we're going to come after TPCH and start publishing some numbers on that as well, which is another one of the big data analytics benchmarks. So we're also very excited about that.
Yeah, we destroyed it. By the way, how many people actually know what TPC XBB is?
We don't know all the buzzwords. Maybe you should start explaining some of those.
Yeah.
But I suggest before you do this, William, we cannot see you currently. We see ourselves. If you can start the presentation so we can actually see you.
Sorry.
Okay.
I was like, that's the best view ever.
Okay, so you were talking.
I see everybody.
So for the other presentation, this is Taurean now showing, and William, say something so you'll appear.
Yes, I'm here. Hello. Testing, 1, 2, 3.
Yeah. Now we see you, so now we can actually see the faces who the people who actually were talking to us all the time. Any more questions, anyone? Come on, otherwise we'll have to hear all of those buzzwords, what they are.
Those buzzwords we're just talking
Nobody
about.
wants that.
Keeping out on benchmarks.
Go ahead.
About the
so
benchmark.
Actually, Taurean was talking about a bunch of like GPUs that NVIDIA has and stuff like that. Can you please tell us, like in very like 2 or 3 sentences, what are the GPUs that you have and what are they good for people who didn't understand? Because you were saying this at the beginning of the talk and you assumed that we know. Some of the people you know. So just don't give us a full talk. Just a bunch.
No. Very simple. We have consumer grade GPUs that are made to. They're primarily there to accelerate games. Their RAM is fast. There's no error correction, and their floating points. They're floating point 64, which is the 64-bit addresses. 64-bit numbers that they can calculate. Those processors are low. Then you get to.
What's the name?
Oh, those are the GeForce line.
Thank you.
There we go. Then we get to the Quadro and Tesla line, which is starting to get enterprise grade, and you're going to see more features and more Float 64 performance, because we want that level of precision, and you're also going to start seeing error correcting RAM. Okay, which means that if an error does propagate, it'll correct. In a GeForce line, if a frame drops, oh well. But when you're doing like massive simulations, you don't want to be off. You don't want that happening. And then we have our embedded line with our Jetsons and our Xaviers, Xavier, Nano, and TX2s. And those are more for embedded systems. They're still extremely powerful. And especially the Xavier line, which is used for like automobile and robotics, that level of use, like industrial size. And they're kind of like, in, I don't want to say they're different niche, I'll say, and their chips serve the purposes that that is necessary. So they also have a different layout of processors for float 32 and 64 shader RTX. I'm done.
For some, no, before you're done, give me one of those models. If I'm gonna go to tomorrow and buy something, I'm a Python programmer, I want to go into machine learning, and I don't know what to buy. I don't want something too expensive, but something that I can run like all of those things you just showed. What thing should I get if I don't know anything? What?
All right. So the good news is this all works on even our consumer hardware. The RAM size, the GPU memory, is going to be what I would suggest you look at if you're budget conscious. Okay. So if the Titan, we always like to say the $2,500 Titan is the best bang for the buck for most consumers, but you can do like a 2060 Super 8 GB or a 2070, or go up the chain if like you're just like, I sometimes want to do this but not really, if you're going to buy. Otherwise, we suggest you provision, or try and go for a Quadro or a GV. Like, then the prices go up, but it's actually more cheaper for you to provision from one of our cloud providers, or from Blazing or Amazon, Google, or GCP, and Azure in our ecosystem.
And when you when the demos you showed us should work on a local GPU, even if you have a machine that just runs games, correct? If it's at least a GPU.
Yeah, you'll get it. Actually, I'm going to pull up a slide just so you can kind of see some things. It's the total cost of ownership. It actually is cheaper to run some of your, even though GPUs cost more, it's actually ending up to be cheaper to run on GPUs because of the speed gains than it is to run on CPU hardware. Let me on GPU only hardware. Let me see if I can find that slide with the thing. But I know Keith is on, and I know he knows the
Okay. We'll put
numbers.
the slide later. For now, when you'll find it, we'll go in. But William, I have a question for William, unless someone else has a question instead of me. Someone else?
I'd be happy to have that conversation about the deeper level of why GPUs are better in this way than CPUs, because I've heard your explanation, like you said earlier, but I'm curious about the deeper architecture and the deeper why the GPU works differently than a CPU.
So this is for Taurean or for William?
It's for anyone who can answer the question.
Okay, William, can you try?
Yeah. So like the thing is, when you look at an entire system, so it's not so much about only thinking about the CPU versus the GPU, because they don't exist in isolation. There's the motherboard, and then there's a system memory and stuff like that. So one of the key advantages about the GPU is simply memory bandwidth. So the speed of GPU memory is way faster than RAM. Maybe the L2 cache of a CPU might be faster, but there's very, very, very little, L2 cache, right? So all of a sudden, you have all this memory that you can then load data onto your processor, process, put it back, and because like when you're processing on a CPU, you're moving data back and forth from your system memory to the CPU doing processing. You might have some stuff in registers, in your caching, depending on what you're doing. But ultimately, you're moving a lot of data back and forth. When you're doing stuff with a GPU, the memory bandwidth is so much faster. Not only that, but you also have, thousands of cores to go do stuff. So if your problem or whatever you're operating on is easily parallelizable, then a GPU is going to be just incredibly performant. Now, there are certain situations where the GPU doesn't excel as much. It's if things that are very, very, very serial in nature, or if you are dealing with so much data that it doesn't even fit in your GPU RAM. Then then the CPU can be a little bit more performant, but even there, it also kind of depends. It depends on what some other components of your hardware architecture are. There's some PCIe buses that can be much faster, like if you have a full, the full 16X, and if you only have a single GPU, it depends on what your bus is, your not your bus, what do you call it, the bridge, the South Bridge, North Bridge. I can never remember which one it is, but anyways, that I think is one of the biggest impacts is in the throughput of being able to process things. Is that people don't necessarily think of, or that it's not immediately obvious. It's not just the petaflops or the teraflops of what your processor has, but also just your memory bandwidth.
Right. So I just want to say it back to you just to make sure I understand. So GPUs basically you can put more data in through it at a time because it's got more memory to hold all that data. And even if it's performing and it has more cores to run on that data. So even
Not
though
necessarily more memory, it's more memory bandwidth.
They almost.
What's the distinction there?
So they almost never have more memory. So they're up. So your question, what's the distinction? Is very important. And they're apples and oranges. So one of the things to keep in mind is you can go to the marketplace right now and buy a motherboard for a computer that has 6 terabytes of RAM.
This is Michael Verhoff speaking, correct?
Yes, but a GPU, right? That's right. Hey everybody. But right now you'll never be able to get a GPU that has 6 terabytes of RAM. So they actually have a lot less RAM, but they use it differently.
So instead of having more RAM, it can change that memory more quickly.
Yes.
Okay.
So it's like having you have a small bucket, but that water, like if you have an aquarium, that water flows through it faster.
Sure.
And now you can kind of clean, if you think about like a water purifier, you can clean more water faster, even though you can't hold as much in storage.
Right. And then since you can put it through the cleaner faster, you can put it into whatever other computation stuff.
That's true, but the RAM is not the important part. So the important part is if you buy a computer right now, a traditional computer, you know how that you can, like, assume you get a computer that has 1 CPU. You can get motherboards that have up to 8 CPUs, but most of the time they're 1. And that little CPU has, on average, around 6 cores, but you can get them with a lot more, 36, 64, if you want to pay a lot of money. But the GPUs can have several thousand cores, but the cores are materially different. And so it's yet again an apples and oranges comparison. A rough approximation, this is very, very rough, but a rough approximation is each GPU core is roughly equivalent to like a TI-80, like a TI-89 handheld calculator. So, but if you have 5,000 of those, and if they're all running at the same time, and they can all access a shared memory buffer, then you can do an awful lot of work.
Michael, it might be easier if you explain what operations the GPU can do better.
Yeah, Michael, before you do this, Taurean, if you can remove the slide so we can see who's talking.
Oh, okay, sorry.
No, you're fine. We just had the slide for a long time. There are several questions that people asked on the chat, so I want to give them priority. We'll get to this, but there are some related. So there's a question about heard that GPU cores are specialized mathematical cores that in general procedures in the CPU. Is this true? This is one. Another one that I still heard that GPU cores have trouble with code branches. If statement, if this is true. And someone else is asking what are the operation performs the GPU in machine learning. And then the question now. So if you can explain a little bit more on GPUs answer all those questions, it will help. And someone talk. I don't know who.
Okay. So I think Jeff, you're talking about, and Mike, I'll give you this. I'll give it back to you in a second. I just want to answer these quickly, and then like we can go back into it because so the mathematical cores, some GPUs have tensor cores, some have most of the processors that you're using right now are what known as shader processors, and that's what you're using to run your calculations. There are tensor cores on some GPUs, and then there's RTX the processors that do the RTX, the ray tracing processors. So there's several specialized, and there's some I don't remember how many FPGAs we have, if we have them in there, but yeah, there's several different specialized computational cores in some of our higher end GPUs. Okay.
Right.
Yeah.
So we haven't talked much about machine learning and deep learning yet. But the first point I want to make is all of the technology inside of a GPU can be used for machine learning.
Yes.
Including ray tracing cores and shader cores. Now that would be really, really weird. And you're not supposed to do that. And there are not easy tools that make that easy to do. So so for all intents and purposes, nobody does machine learning with ray tracing cores. Not yet. They will, but not yet.
Bye, Greg.
Hi, Greg.
Thanks, guys. If you're doing machine learning right now, you're pretty much exclusively using CUDA cores and the newer variant, which is called a tensor core.
So tensor cores are specialized for doing tensor processing. Let me see if I remember correctly. But I'm not contradicting. I'm just basically saying like those particular ones are used for that specialized processor, which is what we're asking. Now, the operations performed by a GPU in machine learning, are you asking for the algorithms or like the specialized math?
I can answer those. In TensorFlow, basically what you do is a lot of matrix multiplication. This is correct. This is mostly what's happening, but there are several specialized functions in some of the machine learning algorithms. I'll make it easy for you. But Michael is right. All of those can be translated to GPUs, and the amazing things that Taurean showed today, and actually the more amazing thing that Williams showed today, Michael didn't show today, William showed today is that those GPUs can actually help with data processing, and this is the key important stuff. And the other thing that Taurean showed is that it can help with other operations not necessarily used for machine learning.
Yeah, so let's see here, heading on. So I'm going through everyone's questions.
List of questions because now everyone's going in the questions. They were quiet before.
Everyone's excited.
Our GPU core varieties still sound all math related. Well, so what? Yes, but and more so. I mean, it's on one hand you could say, well, any computer is math related, but I know that's not what you're saying. So GPUs right now are more math related. CUDA cores and tensor cores prefer very, very well ordered array data. So what they want is they want you to take like a giant pile of data and then chop it up into little chunks that are of equivalent size. With tensor cores, they actually prefer them to be very small integers. Think an 8-bit integer or even a 4-bit integer. If you can get all of the data in your array to be of values that are like less than 127, then the tensor cores will really eat that up. Now, the other stuff, like a shader core, is much more abstract, and the shader cores do not prefer to consume data right out in an array. A shader core is something that pretty much is only used for games, and realistically, nobody in machine learning uses a shader core now. You can, because you can get access to the silicon, but in order to do that, you have to transform your data science project into a project that can be described in the language of shader theory. And most people don't want to do that.
No.
I have one more question to William, if he's still around. William.
I'm still here.
Okay. So tell me more about, like, you work in a company that works with GPUs all the time in their development. What actually
Uh-huh.
do you do like on a day-to-day basis? Do you actually work with the CUDA? Do you work with the higher level instructions? How does development look like from inside the company?
You know, for personally, when we first started, we were doing a lot of our own algorithms. But even still, when we were working more on the algorithms, we were actually leveraging Thrust, which is Thrust is kind of like the standard library, but for CUDA. So like they give you like a lot of like really easy primitives like transform, and you know you can apply stuff, you can filter stuff, and it's makes it so that you don't actually have to work directly with CUDA. It gives you another abstraction layer that makes it really easy. Nowadays, like Rapid started off, I guess, you know, just shy of 2 years ago. We were one of the first contributors to Rapids, and we kind of helped, you know, kick off some of the early algorithms. Because just a little bit of history about Blazing. We used to be Blazing DB, and we built everything from scratch. We had our own file systems. We had our own, like, we built everything from scratch, which is a terrible idea, especially this day and age where there's so much open source stuff. We were thinking about kind of redoing a lot of our things when we found out about Rapids, and so we kind of recreated our product, but based off of the Rapids QDF primitives, and we were contributing to those heavily back then. Nowadays, we don't spend too much of our development time creating and contributing to some of those QDF primitives, but instead we leverage those that already exist and just kind of assemble it to do kind of what it is that we do. We do have some of our own proprietary, like for example, all row-based transformations we have our own like row-based abstract syntax tree parser that does all of those operations. But stuff like joins and group bys and sorting and stuff like that, we leverage QDF for all of those. So for my own personal day-to-day, it's really more about the larger vision of the architecture of how data moves across the execution of a query, and how do we optimize data movement on and off the GPU, and you know, stuff like that. So I used to get a little bit more lower level. Nowadays, I'm more in C++ land, not a lot of CUDA.
Okay. Well, thank you for this. Is anyone, if anyone has, I want to stop the recording at some point, so if anyone has anything to ask that they want on file, now's the time, because we're going to upload it to YouTube later. No one's saying anything. We'll give it first time, second time, third time.
By the way, I do want to say that, like, you know, there's a comment on Colab, and we could have used Colab to do this. And in truth, yes, we could have. We, you know, I'm one of the people who manage the Colab script that allows you to install Rapids on Colab. And I want to give kudos to the Blazing team for what they've actually accomplished, which was a nearly half a minute in, like from sign in to actually get to work, which Colab, it actually takes a few minutes, like more than a few minutes, 8 minutes to actually install Rapids on. So this quick launch system that they're prototyping out and showcasing right now, you know, once they get their load balancing straightened out and everything, is really awesome. Like, it's something we've been looking for almost the entire time of our existence. So, you know, I really do want to thank them for, you know, putting out the resources and the energy to actually spin this up. And this is actually, this is our first time using, at least for me, it's my first time using app.blazing in a larger group. And this is actually pretty fun. It was nice to be able to send you to a link, tell you to git clone, and know that you were there, instead of having it start up, talk for 15 minutes, and then hope that everybody had it installed and got the right GPU and everything else. So kudos to them.
Just a comment. Thanks a lot for that, Taurean. You know, we really are trying to make it like super easy to be able to do, to provide people with GPU-enabled data science environments for them to do stuff. We actually started with Colab. Like we we used to do a whole bunch of Colab when it first started off, and a lot of our demos, we were just like, go to Colab, Colab, Colab. But Colab kept changing so often that everything that we would do with them, it would break after like a week or two. And so we'd have to start our scripts, and it was quite challenging. And I'm sure like Colab also was new for a while, and it was, Colab itself is probably getting more mature, and it'll get more and more and more stable, like if we would have stuck it out with it. But we kind of went and, kind of built our own. And yeah, I mean, this is actually probably the most amount of simultaneous people we've had on app.blazingSQL.com. So hence some of the difficulties today, which I appreciate everybody's enthusiasm for trying it out with us and help kick the tires a little bit. I think that really helped us kind of get a better idea that where we need to improve. I know I'm going to be talking a lot to the team behind our BlazingSQL notebooks and share my experiences today.
Yeah, it's been a really good experience up until like this hiccup. I actually was kind of surprised, but hey, you know what? That's demos, right? And cutting edge technology.
So I actually have.
Don't worry about the loads; they'll be fine. Stick around. I'm gonna finish the recording again. Thank you very much, and stick around.